Turning back to our top story now, Airbus is ordering an immediate software update on 6,000 of its A320 jets around the world.
It was supposed to be a routine flight, just another journey in the skies. Passengers settled in, seatbelts clicked, tray tables up. Somewhere over the Gulf of Mexico, at a calm cruising altitude of 35,000 feet, things took a sharp, terrifying turn. The aircraft, a JetBlue-operated Airbus A320, suddenly pitched nose down without warning, no turbulence, no pilot input, and no time to react. It was fast, violent. A brief but jarring drop in altitude left several passengers shaken and hurt. The flight was forced to make an emergency landing in Tampa, Florida, cutting short what should have been a smooth trip from Cancun to Newark. What caused it? A glitch. But not just any glitch, one buried deep within the aircraft's digital nervous system. What happened on that flight didn't just rattle the cabin, it shook the entire aviation industry because that sudden, unexpected maneuver led to one of the largest aircraft recalls in Airbus history. Right after the JetBlue incident on October 30th, Airbus engineers got to work. What they discovered sent alarms echoing through airliners and regulators worldwide. The culprit was something called the ELAC, short for Elevator and Aileron Computer. This system essentially acts as the aircraft's brain for flight control. It takes the pilot's stick inputs and translates them into instructions for the elevators and ailerons, the surfaces that control the plane's pitch and roll. In modern aviation, systems like ELAC aren't just supportive, they're essential. They're part of what allows fly-by-wire aircraft to fly with such precision. Every small pitch adjustment, every banked turn, every smooth descent is filtered through this system. And because of that, even the smallest misinterpretation inside ELAC can snowball into serious flight behavior. The JetBlue incident made that painfully clear. The engineers didn't waste time. Teams dug into onboard diagnostics, downloaded the black box data, and pored over lines of code. What made things harder was that ELAC had recently undergone a software update, one that hadn't shown issues in simulations or during regular testing. It wasn't until the aircraft was exposed to a unique set of environmental conditions, like elevated solar activity, that the fault became visible. That's the challenge with systems operating at 35,000 feet. They're exposed to forces we don't encounter on the ground. The deeper the engineers looked, the more apparent it became that this wasn't a freak hardware fault or some rare mechanical hiccup. It was software behavior under stress. More specifically, how the ELAC handled corrupted data inputs. Think of it like a GPS giving wrong directions because a satellite blinked. Only now, it's controlling an airplane. Airbus quickly realized that this wasn't limited to one jet. Thousands of aircraft shared the same ELAC variant and the same software version. That meant the risk wasn't isolated, it was global. The system had performed flawlessly for years, but this update introduced a variable that nobody anticipated. What followed was an urgent hunt to determine how many aircraft were flying with the affected code. Airbus coordinated with operators around the world to retrieve software versions and ELAC status. Some aircraft had been flying with the update for weeks, with no problems. Others hadn't yet received it. The goal was to identify risk before it translated into more incidents. Time was now a factor, and the scale was only getting bigger with every hour that passed. In this case, something corrupted that process. Investigators discovered that intense solar radiation may have interfered with the recently updated ELAC software. When solar radiation corrupts data bits in critical flight systems, it doesn't always end in disaster, but it can. And that's the risk Airbus wasn't willing to take. The preliminary assessment showed that under certain conditions, the new ELAC software could trigger an uncommanded elevator movement. That means the aircraft could pitch up or down, all on its own. In the JetBlue case, the autopilot was still engaged during the incident, but it didn't stop the glitch from causing a dangerous pitch-down event. What made this even more unsettling was that the pilots had no control over the initial movement. It wasn't pilot error, turbulence, or weather. The system simply acted on its own. That moment, even if brief, was enough to send adrenaline through the roof. It caught the crew off guard, and passengers too. Some were injured during that sharp descent, and this kind of failure, one that comes from within the aircraft's own software, is exactly what aviation engineers fear most, because it's not just a system reacting late, it's a system reacting wrong. And when that happens, the line between control and chaos gets dangerously thin. The pilots, trained for emergencies, had to make split-second decisions without knowing exactly what caused the pitch down. They weren't fighting weather or turbulence, they were trying to manage a machine that wasn't behaving by the book. Passengers described it as a sudden lurch forward, like the floor dropped out from under them. For some, it felt like a roller coaster drop without the fun or warning. Overhead bins popped open. drinks went flying, and people who weren't buckled in felt the brunt of the dive. Even though the descent only lasted moments, the psychological impact lasted far longer. A sudden loss of control at cruising altitude is one of the last things any flight crew wants to experience. It leaves no room for trial and error. In that instant, the crew had to rely on instinct, training, and limited information, all while keeping the aircraft stable and the passengers calm. After the flight landed in Tampa, the airline initiated a full systems check. But behind the scenes, Airbus and regulators were already treating it as a top-level safety priority. This wasn't about turbulence, wind shear, or a mechanical jam. It was software, invisible, fast-acting, and deeply embedded into the aircraft's behavior. That's what made it so concerning. There were no alarms, no obvious warning signs, just a sudden and unexpected pitch down. And because fly-by-wire systems are so tightly integrated into aircraft control, a software misread doesn't just affect one system, it ripples outward. This is why aviation engineers often refer to software anomalies as silent failures. They don't shout until it's too late, and in this case it shouted just enough to be noticed and just in time to be fixed. But it was a close call, a reminder that in aviation, precision isn't a luxury, it's survival. Commercial aircraft are designed to be predictably boring, rock solid in their behavior. So when a system does something unpredictable mid-flight, even once, it becomes a massive red flag. Airbus engineers dug into the flight logs, the system memory and telemetry data to figure out what happened. What they found was a small but dangerous flaw, a bit of corrupted code caused by solar activity deep inside the ELAC's software logic. The worst part? If the JetBlue flight hadn't experienced that glitch, the vulnerability might have gone unnoticed for much longer. That single incident exposed a flaw that could have led to more serious consequences if left unresolved. That's the reason safety protocols and emergency directives exist, to act before a problem repeats. With modern aircraft relying more on software than ever before, even one corrupted data point can create a chain reaction. And when autopilot is involved, things get trickier. These systems are built to smooth out inconsistencies, but if the data they receive is flawed, they can actually amplify the issue. In the JetBlue case, the autopilot stayed on and followed the corrupted inputs. The result? A sharp, unexpected nose-down maneuver that wasn't commanded by any human on board. That's the paradox of automation. It follows instructions perfectly, even when those instructions are wrong. It's not programmed to question the logic behind the data. It doesn't have instinct or judgment. So when software errors creep in, there's no safety net inside the system itself. And that's exactly what happened here. The autopilot didn't raise any warnings. It just did what it was told. Pilots were left managing a situation that didn't follow any of the usual failure patterns. There were no alarms, no obvious alerts, just a system acting out of sync with reality. That kind of silent fault is especially dangerous. It forces the crew to rely on instinct and manual flying skills, all while under pressure. And as dependable as automation usually is, incidents like this show why human oversight remains absolutely essential. This wasn't about fixing a broken part. It meant rethinking how the ELAC system interprets inputs under abnormal environmental conditions. Solar radiation interfering with onboard computers might sound like something from a sci-fi novel, but it's very real. And this wasn't theoretical. It had just played out at 35,000 feet. Airbus had to act fast, and they did. The recall was issued almost immediately after the investigation results came in. Around 6,000 aircraft from the A320 family were identified as potentially affected. That's over half of all A320s in service globally. The European Union Aviation Safety Agency, or EASA, also didn't waste any time. They issued an emergency directive grounding any affected aircraft until the software was either rolled back or patched, and this wasn't something that could be quietly handled in the background. The fix had to be done before the next scheduled flight, unless the aircraft was being repositioned to a maintenance center. The impact? Massive. Planes grounded, flights delayed, thousands of passengers stranded across multiple countries, all during one of the busiest travel weekends of the year. The fix itself wasn't complicated, but it required time. For about 2/3 of the affected aircraft, the solution was rolling back to a previous version of the ELAC software. That could be done in a couple of hours, but for the remaining jets, especially older variants, the repair involved a hardware swap. That meant longer downtimes, more logistics, and even more flight disruption. Airlines across the world scrambled. American Airlines had around 340 aircraft that needed the fix and moved quickly to get most of them back online within days. Lufthansa, Indigo, EasyJet all had planes taken out of rotation. Avianca in Colombia was hit especially hard, with more than 70% of its fleet affected. They had to stop selling tickets until December 8th just to cope with the backlog. For airlines already struggling with engine part shortages, labor gaps, and rising passenger demand, the timing was terrible. Maintenance teams had to work around the clock, scheduling teams scrambled to reshuffle crews and routes. Passengers called in with rebooking requests that flooded airline systems. It was a full-blown operational nightmare. Some airlines managed to patch aircraft between red-eye landings and morning departures. Others weren't as lucky. Hangar space became a bottleneck, with long queues forming at major service hubs. In regions where airlines operated smaller fleets, grounding even a few planes threw entire flight schedules into chaos. Public advisories were issued. Air New Zealand and Volaris warned of delays stretching several days. Air France had to cancel 5% of its daily flights. ANA grounded 65 flights in a single weekend. Finnair delayed takeoffs while pilots checked their onboard software versions. The ripple effects were felt everywhere. Indian carriers were hit too. The DGCA stepped in, ordering all A320 operators in the country to ground affected planes until fixes were confirmed. Indigo had 200 aircraft impacted, but by the time the directive came out, they had already updated most of them. Air India reported 113 aircraft affected, and Air India Express had to deal with delays across 8 flights while working on upgrades. The recall was now being called one of the largest in Airbus's history. The scale was staggering. Airlines were already bogged down with existing maintenance backlogs. The sudden grounding of thousands more aircraft added to the chaos. Repair facilities were overbooked, staff were overworked, and still, the work had to be done. The ELAC computer, it turned out, had simply not been stress-tested enough against solar radiation interference. Thales, which manufactures the hardware, stated that their systems met all Airbus requirements, and they did. The issue wasn't the hardware, it was how the newer software update responded when exposed to radiation anomalies. It passed standard checks, but not the edge case scenario that actually happened. Solar radiation isn't something commercial aviation deals with often, but every so often it becomes a real threat. The sun throws out bursts of energy that, if strong enough, can corrupt data in flight-critical systems. In the case of the JetBlue flight, it was enough to cause the ELAC to misread and misfire. The result? That unexpected, dangerous pitch-down moment. This isn't about pointing fingers, it's about how software and hardware interact under real-world pressure. Airbus and Thales had to work together non-stop, coordinating with airlines across the globe to roll out fixes safely. Thousands of updates, installations, verifications, all happening while air traffic continued to move. The takeaway is hard to ignore. Even with today's technology, even with millions of hours of testing, something as unpredictable as solar weather can still find a crack in the system. And when it does, the consequences stretch across the globe. And here's the part that really hits. If this flaw had remained hidden, another aircraft could have faced the same problem, maybe without a safe ending. Airbus's internal bulletin didn't sugarcoat it. Worst case scenario? An uncommanded elevator movement strong enough to exceed the structural limits of the aircraft. That's not just a hard landing, that's a catastrophic failure. So regulators acted fast. ESA grounded the aircraft, airlines followed the directive, and most importantly, Airbus didn't wait to be pushed. They took control of the situation from the start. That's likely what prevented a second, possibly deadlier incident. The A320 is a giant in the aviation world. It recently overtook the Boeing 737 as the most delivered aircraft in history. It's the backbone of global short-haul travel. So when it hits a bump, even a small one, the entire industry feels it, and while no one wants to hear that a software update caused a flight control issue, the response this time was different, quick, open, and effective. There was no denial, no slow walking the solution. Everyone involved knew what was at stake and acted accordingly. It's a sharp contrast to the Boeing 737 MAX crisis years ago. Because in aviation, one small vulnerability, even something as unexpected as solar radiation, can have global consequences. If you found this deep dive helpful, be sure to subscribe for more updates on aviation, tech, and everything in between. Hit the like button, share with a fellow traveler, and drop your thoughts in the comments, especially if you were impacted by the A320 recall. Stay safe, and see you in the skies.